Hello everyone. In this video, we are going to talk about concavity and inflection points. So when we talk about a graph, we could talk about the shape of the graph. Is it concave up or concave down? So concave up is going to be shaped kind of like this, whereas concave down is going to be shaped more like that. And we use the second derivative to help us determine that. If the second derivative is positive, then we're going to be concave up on that interval, whereas the second derivative is negative implies that we are going to be concave down. Anywhere we change from concave up to concave down or vice versa is going to signify that we have something called an inflection point there. So let's look at a few examples. Let's look at this one. We want to determine concavity for this graph. So we're going to take the first derivative, so 3x squared minus 18x plus 9, and then we're going to take the second derivative. So we have 6x minus 18, and we're going to set that second derivative equal to 0. If we divide by 6, we're going to get 3. So now we're going to test the second derivative using a sign chart. So notice I labeled this sign chart for the second derivative. Our sign chart is going to use the domain of the original function. This is a polynomial, so it goes from negative infinity to infinity, and 3 is the only value that's going to go on there. So this guy has a name, and we call it possible inflection points. So I'm going to call those PIPs for short, or PIPs for short. So we're going to test that second derivative. Just like we did with the first derivative, we're going to pick numbers in here. So I'm going to pick 0 on the left and maybe 4 on the right. And all we care about is the sign. It's going into the second derivative. So 6 times 0 minus 18. And that's going to give us a negative value. And when we plug in 4, we have 6 times 4 minus 18. And that's going to give us a positive value. So this function is concave up from 3 to infinity because that second derivative is positive, whereas it's concave down from negative infinity to 3. Because we're changing from concave down to concave up, then we do have a definite inflection point. So I'm going to notate that as IP at x equals 3. If we wanted the y value associated with that, we could plug that 3 in here. Let's look at another example. So we're going to find the first derivative. So we have a minus 3x squared plus 3x plus 18. And then we're going to find the second derivative. So minus 6 times x plus 3. And we're going to set that second derivative equal to 0. So 3 equals 6 times x, which means x equals 3 over 6. And we can reduce that to 1/2. So this is a possible inflection point. To find out if it's an inflection point, we are going to plug in, create a sign chart for the second derivative. The domain for this function is all real numbers. 1/2 is going to go on my sign chart, and we are going to test. So let's plug in 0. It goes into that second derivative. So negative 6 times 0 plus 3. That's going to give us a positive. And then we can plug in something bigger than 1/2, like 1. And we could pick any number on this side. So negative 6 times 1 plus 3. That's negative 6 plus 3, which is a negative. So this graph is concave up from negative infinity to 1/2. And it's concave down from 1/2 to infinity, with an inflection point happening at x equals 1/2. So that's how we can use the second derivative to look at concavity. Now there's one more use for the second derivative, and this is the formal second derivative test. We can combine these ideas of concavity with the fact that if we have a min or max, it has to happen at a critical number. So the second derivative test allows us to look at whether we have a max or min by plugging numbers into the second derivative. So this is another way to tell, or to find, I guess would be a better way to say that, local extrema. So what it says is you find critical numbers, and then we are going to plug critical numbers into the second derivative. That second derivative does need to be continuous over the interval that contains our critical number. If that second derivative is positive, then what that means is this graph is going to be concave up, and it's concave up, it looks like this, which means that at that C value, there has got to be a minimum. Whereas if that second derivative is negative, then we are concave down. And if we're concave down at that critical number, then we have to have a maximum. If, however, we get 0 for that second derivative, then the test is not going to be conclusive. And what that means is we have to result back to the first derivative for test. Now, typically when I'm working problems like this and I need to know increasing, decreasing, maxes and mins, I use the first derivative test. Sometimes the second derivative is nice and we could find those answers pretty quickly. Sometimes it's not as useful. So let's look at an example. We're going to use the second derivative to find all local extrema, and then we're going to find inflection points. So we're going to use the second derivative for two uses here. So let's find it. Our first derivative is 5x to the fourth minus 15x squared. I'm going to go ahead and find that second derivative. So I'm going to have 20x cubed minus 30x. Before we do go any further, we need to find critical numbers. So to find critical numbers, we're going to set that first derivative equal to 0. So 5x to the fourth minus 15x squared is going to be equal to 0. We can factor out a 5x squared. That's going to leave us with x squared minus 3. And we're going to set each factor equal to 0. So we're going to get x equals 0 here. And we're going to get x equals plus and minus square root of 3 here. Okay, notice that first derivative is defined everywhere. So, and that's because it's a polynomial. So we don't have any places where the derivative is undefined. So how would we use the second derivative test? We're going to use it for extrema. So second derivative test says take your second derivative and plug in your values, and that's going to tell you about concavity at that point in time, and then we can figure out what's happening with extrema at that moment in time. So here's my second derivative. So when I plug 0 in, I'm going to get 0. What that means is the test is inconclusive. So we are going to have to use the first derivative test to figure out what's going on at 0. And we'll do that in just a minute. So now let's plug in the square root of 3. So we have 20 times square root of 3 cubed minus 30 times square root of 3. So when I plug this in, I got a positive 51.9. So this is positive. So here's what this means. We are concave up at x equals square root of 3 because that second derivative value is positive. We're concave up, we're shaped like this, which means there has to be a minimum at x equals square root of 3. And then we're going to do the same thing here with the negative square root of 3. We have 20 times negative square root of 3 cubed minus 30 times negative square root of 3. I'm going to plug that in. I'm doing that off screen. And I ended up with a negative 51 and some change, which means this graph is concave down. And since it's concave down at negative square root of 3, it looks like this, which means we have to have a maximum at x equals negative square root of 3. Now we're going to compare that with the first derivative test. So the first derivative test, and I'm going to have to rewrite my derivative here. So this is f prime of x equals 5x to the 4th minus 15x squared, which is 5x squared, x squared minus 30. So I started with a polynomial, domains all real numbers. We ended up with negative square root of 3, 0, and square root of 3. So square root of 3 is about 1.7. So let's test some values and we'll compare what's going on. So let's plug in something over here, like negative 2. So I'm going to have 5 times negative 2 squared times negative 2 squared minus 3. So positive times a positive times a positive is a positive. Let's plug in a negative 1 to test this interval. 5 times negative 1 squared times negative 1 squared minus 3. Positive, positive. This would be a negative. Let's do a positive 1. Positive, positive, negative. And then let's try positive 2. Positive, positive, and positive. So we said, we'll go ahead and do increasing and decreasing also. You're increasing from negative infinity to negative square root of 3. Look what's happening around 0. It's decreasing to the left and to the right, even though there's no discontinuity here. We could write that decreasing interval from negative 3 to 3, and then increasing from square root of 3 to infinity. So what's happening? We have a maximum at x equals negative square root of 3, and a minimum at x equals positive square root of 3. And that's what we said with that second derivative test earlier. Now let's analyze using that second derivative. We're going to look at concavity. We haven't done that yet. So I'm going to have to rewrite my second derivative down here. My second derivative was 20x cubed minus 30x. So we need to find possible inflection points by setting this equal to 0. So I'm going to factor out a 10x. And that's going to leave me with 2x squared minus 3. X is going to be plus or minus square root of 3 over 2. And then we are going to create a sign chart for the second derivative. Again, the domain of the original polynomial is all real numbers. We're going to put in negative square root of 3 over 2 and positive square root of 3 over 2. So Square root of 3 divided by 2 is about 1.2. So what am I going to use for test values? We could use -2, 0, and +2. And that's going in here, that second derivative. So 10 times -2 times 2 times -2 squared minus 3. So negative, positive, negative, and this would be 8 minus 3, which is positive. So positive here. When we plug 0 in, oh no, I forgot to put 0 as a critical number on here. I got so concerned with what was going on this right. I'm sorry, not critical number, possible inflection points. So let me correct what's going on here. I need 0 there, which means I cannot test 0. So let's test a -1. So if I plug in -1, I have 10 times -1 times 2 times -1 squared minus 3. So positive, negative, and this would end up being a negative, which would make that a positive here. And then let's plug in something on this interval, like 1. So 10 times 1 times 2 times 1 squared minus 3. Positive, positive. This would be a negative. And then something over here, like 2. Positive, positive, positive. All right, something doesn't feel right with this over here. So let me go back and check some things. When we plugged in that -2, we had 10 times -2 times 2 times -2 squared minus 3. So we had 10's positive, -2 is negative. This would be a positive 8 minus 3. Positive times a negative times a positive is a negative. And then let's just check these real fast. Positive, negative, negative would make that positive. And then we've got a negative, then a positive. So let's talk about concavity. Where are we concave up? Where are we concave down? We are concave up from negative square root of 3 over 2 to 0. And then from square root of 3 over 2 to infinity. We are concave down on those other intervals, negative infinity to negative square root of 3 over 2, and then 0 to square root of 3 over 2. So we do have some inflection points. They are happening at x equals negative square root of 3 over 2, 0, and positive square root of 3 over 2.